Hello everyone and welcome to Lesson 8 of the Physics Summer course. Today we're going to be talking about momentum, and this is going to be the last lesson of the summer. So thank you for everyone who stuck with it this summer. After today I'm going to give you the final homework, and I'm also going to give you a survey they'd like you to fill out to see how I did this summer. And of course I know I did great, but now you need to tell me so I can boost my own ego. But really, please be honest. So first, I'm sure momentum is one of those topics in physics that you've heard of before. Like, for instance, you've heard of forces, you've heard of friction, you've heard of energy, but maybe you don't know what momentum really is when it comes to physics. And here's where I'm going to tell you, momentum, when do you use it? You're going to use it for collisions and explosions, two of the most exciting parts of physics. And in my opinion, and just in general, students typically get the highest grades in the momentum portion. Probably because the only way you can, not the only way, but the hardest part for momentum is remembering positives and negative signs. Because, believe me, it sneaks up on you the first couple times. You will get a couple questions wrong today that you shouldn't, and that's okay, because I'm going to correct you and make you feel dumb. So, with momentum, let's start with the equation for momentum. Momentum is defined as P equals mv. That's right, P stands for momentum, because mass was taken already, so you couldn't use m. And so we went with the next logical letter, which is p, which has nothing to do with momentum, but I think has something to do with the Greek word for momentum, which I don't know what that is, but that's what I've been told. Anyways, p, momentum, is equal to a mass times your velocity. It's mass times velocity. Pretty similar to force, because force is mass times acceleration. And as a matter of fact, if you were in my calculus class, not that I'm saying you are, but if you were in my calculus class, I would tell you that force is the derivative of momentum. Now, don't think about that too hard, because that would completely mess up everything we're doing today. Calculus doesn't really scale the same way physics does. In other words, even though I'm saying it's the derivative, it has nothing to do with the derivative. At risk of confusing you anymore, I'm just going to continue. The only other thing I want to say about momentum right off the bat, the units are like the worst units like in all of physics. It's the kilogram meter per second. And the reason why I say it's the worst units, at least for the summer course, is because every other unit has been simple up until this point. I mean, even something like kilogram meter per second squared, which is the same thing as the Newton, at least you can call it the Newton. It's got that nice abbreviation, Newton. What's the abbreviation for momentum for kilogram meter per second? Nothing. Which is why I, Dan the tutor, am trying to get my own unit named after me. I am trying to call this the W, which stands for Wiesner, and the symbol is a cursive W. So those are the units I'm going to be using today, and I encourage you to use when you take your test in the fall, so that way we can spread the word of Dan the tutor. And your teacher will ask you, why'd you write a cursive W? And you'll tell them, because that's what Dan the tutor, the greatest tutor in the world, told you to do. And they'll say, well then here's 100% on the test. So I assume that's how that will go, so I encourage you to try that out. The last kid didn't, for whatever reason, but you can change the future. Anyways, we have conservation of momentum, which is going to be very similar to conservation of energy, which we talked about last week and the week before. The difference is between conservation of energy and conservation of momentum. Momentum is going to be always conserved as long as you have two objects involved. Technically, it can be more than two objects, but for the examples we're looking at today, we're just going to be looking at two objects. And if you do have two objects, then, like for instance, block A and block B down below, momentum is going to be conserved. You don't have to worry about friction. You don't have to worry about anything else. P total 1 equals P total 2. I'm also going to call it like initial and final, really, today. I'm not going to call it 1 and 2. But what I'm saying is, if you have object 1 with mass 1 and velocity 1, it must equal mass 2 with velocity 2, assuming that it undergoes some kind of change. Now, most of the time, this isn't the case. This is actually kind of a bad equation, because most of the time we are going to have two objects with their own mass and velocity. As an example, just look at what I set up for this equation right here. I would say that mass A times velocity A plus mass B times velocity B, and this is all the initial momentum. Like I'm saying, P total initial equals all this stuff. I have to consider both boxes, because they both have a mass and they both have a velocity. I'm going to have to add them together when I give them numbers. And then what I'm saying is I can compute the P total final by doing the exact same thing, mass A, velocity A, plus mass B, velocity B, Just remember that the velocities will very well change in the final scenario. And oftentimes I even like to draw a picture of this. Like here's box A, here's box B, and now after they collide, maybe they're going in opposite directions. They don't have to go in opposite directions, but a lot of times they do. That's why I'm drawing this. I'll give you a second to catch up with the writing, but in the meantime, are there any questions? And like I said before, momentum is usually one of the easiest topics that students find, especially after we've spent a lot of time working with complicated equations like forces and energy. Momentum is going to be kind of like a nice break halfway through the year. As a matter of fact, it was the only test in high school I got 100% on. As smart as I was back then, this was the only one that I got 100% on. And actually, I remember it distinctly because our teacher would let us give a note card that we could write anything we want on it. And I remember for that test, I literally just wrote one thing on the note card, and it said, "Don't make stupid mistakes." And that was the only time I wrote something like so simple on a note card, and that was the one time I didn't make silly mistakes. So there you go. I did what I said. So anyways, now we have the three types of collisions. There's elastic, inelastic, and perfectly inelastic. An elastic collision is where momentum and energy are conserved. Momentum and energy are conserved. Now, what does that mean to you? It means two things. Number one, it means P total initial equals P total final. P total initial equals P total final. It also means that E, energy total initial, equals energy total final. And most of the time, for momentum, we're talking about just kinetic energy. There's going to be no difference in heights. We're talking about flat surfaces. So if you add up all the energies in all the boxes for the kinetic energy, they should equal each other in an elastic collision. Next, we have the inelastic collision. This is where momentum only is conserved. Momentum only is conserved. And what that means is that only P total initial equals P total final. By the way, if the problem never says if it's elastic or inelastic, you're going to assume it's inelastic, which is why I call this the default case. It's the default case. If the problem doesn't tell you about energy, just assume it's not conserved. Just use this equation only. And then the last case we have is perfectly inelastic. This is an interesting one. This is where momentum is conserved. Momentum is conserved. And the objects stick together. Momentum is conserved and the objects stick together. And what that looks like as far as the equations go, you're again going to write P total initial equals P total final. And there is one more thing it means, but we're going to wait until we get to that problem before I explain it, because it's kind of hard to explain in words. It's better to just look at the example. But are there any questions on the three kinds of collisions? One more thing I want to say. You'll notice for all three of these collisions, they all have something in common. Momentum is conserved for all of them. And that's because, like I said earlier, momentum is always conserved as long as you're looking at two or more objects. So let's go ahead and look at number one. A 2 kilogram block has a velocity of 10 meters per second and is heading towards a stationary 5 kilogram block. The two blocks collide, and after the collision, the velocity of the 2 kilogram block is now 2.5 meters per second in the opposite direction. What is the velocity of the 5 kilogram block? I love drawing pictures for momentum problems. I think it'd be silly not to. So first I've got the 2 kilogram block. That's heading 10 meters per second in the positive direction, which we'll say is to the right. And then that's heading right for a 5 kilogram block, but it says that one's stationary. I'll write V equals 0. So this is all the initial case. This is the initial. And then for the final, it says that the velocity of the 2 kilogram block is now 2.5 meters per second, but in the opposite direction. 2.5 meters per second to the left. And then for the 5 kilogram block, well, that's the velocity that we're going to be solving for. I'm assuming it's moving to the right, but technically I don't know that yet. And we will find with the answer whether it's positive or negative. If it's positive, it's moving to the right. If it's negative, it's moving to the left. So we're going to definitely assume we're getting a positive answer. But if we get a negative, then you would just say to the left. So now I'm going to set up the equation that I said from earlier. I'm going to say P total initial, which over here, that's going to be the mass times velocity, which is 2 times 10, and a positive 10 because we're going to the right, plus for the 5 kilogram block, mass is 5, velocity is 0. Technically, I don't even have to write the 5 times 0 because anything times 0 is 0, but it's going to be 20 for the initial momentum. So that's 20. And then for the final momentum, P total final is equal to negative 2.5 times 2. Why negative? Because we're going to the left. As a matter of fact, in your picture, if you want to draw negative 2.5, I'm okay with that. Personally, I don't because I just see left and I know it's negative. But if you want to draw negative, I don't care. Be my guest. And then finally, plus 5 times the velocity v. And v is the variable we're solving for because we don't know what that is yet. And now that I have my P total initial and P total final, I can set them equal to each other and I can solve them. So I'm going to do that on a separate sheet of paper. Let's say I've got 20 from the initial equals negative 2.5 times 2 is negative 5 plus 5v. Add 5 to both sides. That's going to give me 25 equals 5v. Divide both sides by 5. Looks like I get v equals 5 meters per second. And the fact that it's positive tells me it's moving to the right. Any questions on that one? Okay. Next, part B. The question asks, what type of collision is this? We remember there's 3 kinds of collisions. Basically, I know immediately it's not perfectly inelastic. Why not? Because these objects are not sticking together. The 2 kilograms going to the left, the 5 kilograms going to the right, they don't stick together. It's not perfectly inelastic, but it still could be elastic. In other words, energy is conserved. How would I know? Well, let's actually find the energy in the initial and the final case. So E total initial equals 1/2 mv squared, because it's kinetic energy, 1/2 times mass 2 times velocity was 10, and that's squared. You square the velocity. And then let me just quick plug this in a calculator. You get 100, not that bad. And then for E total final, this one's a little more annoying, but we can still do it. I'm going to give myself more room because this is actually kind of long. But it's going to be E total final equals 1/2 mass, which is 2, times velocity, I'm talking about the 2 kilogram block still, negative 2.5 squared, and then plus 1/2 times 5 times velocity 5 squared. So there's the setup, and now I can just plug this entire thing in a calculator and I'll get my answer. But before I do, one thing I just want you to notice is the fact that, see how the velocity is negative for one of the parts? Well, since you're squaring it, it's not going to be negative, it's going to be positive. So in other words, you should never have a negative energy, it should always be positive. Anyways, you plug this in a calculator, you get 68.75, and the units are joules for energy. Same was true for the 100 joules. Now, I'm going to say this, I look at this and I say, well, the energies are not equal to each other, therefore it must have been inelastic. If it was elastic, the energies would have equaled each other. And that's it for that one. Any questions? Okay. Next, we have a fun one, number 2. A marksman is doing some target practice with a block of wood, mass 10 kilograms. The gun has a mass of 4 kilograms, and it is completely still when it is fired. The bullet has a mass of 100 grams, and it exits the gun with a velocity of 100 meters per second. After the bullet is fired, the gun has some recoil in the opposite direction. What is the recoil speed of the gun? So here's what I'm going to say for this one. Basically, let me draw a picture, okay? We've got the gun. We've got the bullet. It says the bullet's 100 grams. I give that to you on purpose to trick you. You need to convert that to kilograms. We cannot use grams in this class. How do you convert to kilograms? Divide by 1,000 because it's kilo, and that's 1,000. So you'll get 0.1 kilograms. There we go. So that's 0.1 kilograms going to the right at a speed of 100 meters per second. And we want to know what is the recoil speed of the gun. Obviously, we're going to use momentum. P initial equals P final. So if this is the initial picture, can someone tell me what the final picture will be? Yes.
I don't think I know.
You are correct. You don't know because it's a trick question. Why is it a trick question? I said this is the initial. I lied. This is actually the final picture. Then what's the initial picture? The initial picture you're going to do before anything was fired at all. It was just it was standing still. And I know that's kind of tricky, but now you see the trick coming in the future, so I can get away with that once. Anyways, the initial picture, nothing's moving, all the velocities are 0, which means P total initial is 0. And can the momentum be 0? Yes, because it is right now. All the velocities are 0. Which means the final momentum must also be 0. But how can that be 0 if the bullet's being fired at 100 meters per second? It's because the velocity of the gun going backwards, the two momentums are going to cancel each other out. And as we probably can figure out, the mass of the bullet is extremely small, but its velocity is really high. The opposite's going to be true for the gun. The gun has a very large mass by comparison, but it's going to have a very small velocity in comparison to the bullet. So what I'm going to say is P total final is equal to, first I'll do the bullet, which is 0.1 kilograms times 100 meters per second. Remember, momentum is just mass times velocity. And then I'm going to say plus the momentum of the gun, which is a mass of 4 kilograms times a velocity v. I don't know what the velocity v is, but I do know this. It's equal to 0. And I also know that velocity is going to be negative, and the reason why is because I know it has to be negative to cancel out the forward momentum of the bullet. Any questions so far before we do the math? So now this part isn't too bad at all. You just do 0.1 times 100. You'll get 10. And then plus the mass of the bullet is 4 times v, and that equals 0. So then subtract 10 from both sides. 4v equals negative 10. And v is going to be negative 2.5 meters per second. Like I said, it was going to the left. Now you got to be careful. Don't circle negative 2.5 as your final answer. Why not? Because I asked for the speed, and speed is always a positive number. Speed is just the magnitude, no direction. So in other words, just say 2.5 meters per second, circle it, and now you're good. Any questions on 2A? Okay, now for part B, we're going to be continuing the last problem. The bullet, remember this is a marksman firing a bullet at a block of wood. The bullet becomes firmly lodged within the block of wood. What is the speed of the wood and bullet after the bullet hits? So notice the gun's not even in the picture anymore. So when I draw the initial is going to be the bullet right before it hits the block of wood. Again, the bullet 0.1 kilograms, same speed, 100 meters per second is the speed of the bullet. The mass of the block is, I think it was 5 kilograms. 4 kilograms, never mind. That's 4 kilograms. Or was that the gun? It might have been the gun. Oh, the gun is mass 4. Do I even give a velocity? Do I give a velocity?
Yeah, it says mass 10 kg.
Ah, thank you.
In the parentheses.
I should know this. I made the problem. Thank you. So 10 kilograms, and that speed is 0 because we don't know it. And then for the final momentum, I say that the bullet is inside the wood. Something like this, okay? And now they're moving together with some unknown speed that we're going to solve for. And like literally my picture took up like all this space, so now I have to do like the entire thing on scratch paper. That's okay. So first I'm going to say for the initial, it's mass times velocity, 0.1 times 100, that's for the bullet, plus mass of the wood, 10 times its velocity, 0, 0. And then when I set it equal to, well, the final scenario, basically, well, I guess first plugging this in a calculator, you get 10. Not too bad. Then for the final scenario, P total final, what's the mass going to be?
10.1 kilograms?
Yes, 10.1. And that's because we added the mass of the wood, which is 10 kilograms, and the bullet, which is 0.1, for a total mass of 10.1 kilograms. That's exactly what you want to do. And then times some velocity v. Can someone tell me what kind of collision this is?
Is this the perfectly inelastic?
This is the perfectly inelastic. And the reason why is because the bullet and block are stuck together. They're moving together. Now, that's why I kind of skipped that part earlier, is because what changes with the equation? Nothing. You just added the masses together. It's still the same equation as before. So now I'm just going to set these two things equal to each other. 10 equals 10.1 V. Divide both sides by 10.1. And I will get V equals 0.99 meters per second. And it's positive because it's to the right, which makes sense. Any questions on that one? Okay. Number 3, I really like number 3. You probably won't. There's a lot of variables involved. Number 3, a block of mass m is at rest when it is struck by another block of mass 2m traveling at a speed of v. Let me just draw this right now so you're not super confused. So it says some block m is at rest, no speed, and then 2m is going to be crashing into it with speed capital V. Okay. After the collision, the block with mass 2m is stationary, and the block with mass m is now moving with an unknown speed. Is this collision possible in real life? In other words, are we breaking any laws of physics with this collision? Kind of vague what I mean by that, but hopefully you realize, is momentum conserved? So anyways, let's see. After the collision, 2m is here, speed is 0, so v equals 0. And then little m is now moving with some unknown speed. Let's see if we can calculate it, even though there's all variables here. So first, I would say P total initial is equal to the mass, which is 2m, times velocity v, and then since the other one's at rest, I don't even have to include it. It's going to be 0. Then for the other picture, it's P total final is equal to, now the 2m is 0, so I won't even include that. And the mass of the other one is mass m times velocity unknown. I'll call it vf because I'm solving for it, and I want it to be different than v. So now I'm going to set these two things equal to each other. I'm going to say 2mv equals mass times v final. Mass cancels out, and I would say the final speed is equal to 2v. Can someone tell me what that means in English?
That means that the final velocity equals 2 times the initial velocity of
Exactly.
of the 2m.
Yes, exactly. So whatever this speed was, you can plug in any speed you want. 10, 20, 1 million, whatever it is, this speed's just going to be double it. So good. It looks like we didn't break any laws of physics, and this collision is possible in real life. Except, you forgot one thing. Let's just see what happens when I check the energy on this. Okay, let me just check the energy. I just have a feeling about this one. Funny feeling. E total initial, it's 1/2 mv squared, so 1/2 times mass 2m times its velocity, v squared. The 1/2 and the 2 cancel, I just get mv squared. That's okay, nothing wrong with that. Now let's look at E total final. E total final, it's 1/2 mv squared. The mass is only little m this time, but the velocity is 2v squared. And when we square that, we have to square both quantities. So in other words, it's going to be 1/2 times 1/2 m times 4v squared. And if you reduce that, 1/2 times 4 is 2 mv squared. And now I have a problem. Remember, the initial was mv squared, and now our energy is 2 mv squared. You know what just happened? The energy doubled. Can energy double? No, you just created energy. So the answer is no, this is not possible. If you were to ask what kind of collision is this, elastic, inelastic, or perfectly inelastic, I would say none of the above. Impossible collision. And I've literally seen questions like this in college and high school. So be prepared for this kind of question. This is what they mean when they say, is it possible?
So I have a quick question.
Go ahead.
So we had a different example where we went from 100 to 68.75, but you can never have more energy than you initially started with, but you can always have less than you initially started with.
That is a very good question, and you're right. Yes, you can lose energy because energy is not really lost. It's just converted to heat and sound. But you can't gain energy unless there's an explosion, and we're not talking about that right now.
Cool.
Like, I don't think when these boxes collided, this was an explosion. But having said that, I have seen examples, like, for instance, like a rocket, breaking apart into its main thruster and its boosters. I have seen that, and that would be like an explosion. Or there's a few examples where it does work out, but this is definitely not one of them. So now, for the very last topic we're going to talk about this summer, it's momentum and impulse. Like I mentioned before, momentum is always conserved as long as you have two objects. However, if you only have one object, and I'll give some examples, then that means we're going to use momentum and this thing called impulse. Now, let me give you just some quick examples. Let's say you punch a wall, right? And your fist has some mass, let's say like 5 kilograms, and you punch the wall with a speed of 10 meters per second. Assuming the wall is like, concrete or brick, does the wall move? And the answer is yes. Actually, it does move. How far does it move? Well, it probably moves, assuming the mass of the wall is like, 20,000 kilograms or something like that. The wall probably moves 0.000000001 meters per second. In other words, you probably don't notice it. And so for that reason, and the example, if you read this in the paragraph here, basically I say the same thing is true when you jump off the earth. Literally, you can jump right now. And when you jump off the earth, does the earth move? And the answer is yes. But since the mass of the earth is 6 times 10 to the 24th, it would take me a while to include how many zeros until you actually, get the 0.0000001, whatever it is, meters per second that the earth actually moves. So, in other words, yes, when you jump, you move the earth. Is it noticeable? No. For that reason, a lot of times, we don't want to include the other object because one is significantly bigger than the other. Most common example I see is a wall. And so for that reason, we have this thing called impulse where we don't want to set the momentums equal to each other. Then what do we want to do? Let me show you. The equation for impulse, this is going to be fun. The equation for impulse is, the symbol is J. You may be wondering, why can't we use I? Well, obviously I was already used for moment of inertia, which is something we have not even talked about this summer because it's related to torque, which is something else we have not talked about this summer. Basically, if there was a week 9 or week 10 to this summer course, we could have got to torque, but that's okay. We don't need torque. Impulse is equal to J because we ran out of variables, and the equation for impulse is delta P. Now, I've mentioned this before. I do not like delta notation, so instead I'm going to write P final minus P initial. Now, normally, this quantity should be 0. Why? Because normally P final has to equal P initial. In other words, if the final was 100, the initial is 100, and the impulse is 0. That's why when you have two objects, the impulse will always be 0, but when you have one object, it's not going to be 0, as we will soon find out. The other fun thing about impulse is it's one of the only things in physics that has two equations. The other equation for impulse is force times time. And as a matter of fact, we're going to be setting these two equations equal to each other in a few minutes. And finally, the units for impulse, they're the exact same as momentum on the other page, kilogram meter per second. We also have the added units of Newton's time seconds because the units of the force is a Newton and units of time is seconds, so Newton's time seconds. And again, of course, I'll accept the Wiesner, and yes, I will be accepting it on your homework as well. So, make use of that. So any questions on the equations before we go into the final examples of the summer? Okay. It's funny, I remember when I started these summer courses, it was still light out by the time I finished the 7:30 lessons. Now I have to put my light on. And those of you watching the recording, you have no idea what I'm talking about, but that's okay. Number 4, a 2-kilogram ball is thrown against a wall with a speed of 12 meters per second. The ball bounces off the wall and has a final speed of 7 meters per second. Part A, what is the magnitude of the impulse from the wall on the ball? Once again, I'm going to draw a picture of this. I have a ball, that's my wall. I have a ball coming in at 12 meters per second. The mass of the ball is 2 kilograms. It bounces off the wall and comes back with a speed of 7 meters per second. Now, obviously, there's two objects here. It's the ball and the wall, but I'm not counting the wall. I don't have the mass of the wall. I'm assuming it's really big, and especially because I'm talking about impulse, the one object I'm talking about here is obviously the ball. So what am I going to do? Well, I can either use delta P, P final minus P initial, or I can use force times time. Here's an idea. Do we have force? No. Do we have time? No. Should we use that equation? Absolutely not. Let's use P final minus P initial. So the mass is 2 times P final. That's the 7. That's the 7. So 2 times 7 minus mass initial is 2 times velocity is 12. Okay, and if we plug this in a calculator, we'll get 14 minus 24, and we get negative 10. And that's the wrong answer. I tricked you. Can someone tell me why that's the wrong answer? So the answer is, what did I say at the very beginning? That momentum's like the easiest thing, except the one thing you could mess up is that you miss a negative somewhere. You see that velocity coming back? Well, that certainly is negative because it's going to the left. And so it's actually negative 7. Well, it doesn't matter if you put the negative here or in front of the 7. It's going to be negative either way, which means it's negative 14 minus 24. The final answer is negative 38 kilogram meter per second, and I'm smushing the units here, but whatever. Negative 38 is the answer. Oh, and I shouldn't circle that because see how I'm asking for magnitude? Well, magnitude is the size only, not the direction, so 38 kilogram meter per second.
Wait, why are they both negative?
They're not both negative, let me be clear. It's P final minus P initial.
Yep. Yeah, no, I understand now, thanks.
Yep. Okay, good. Any other questions? Okay, now part B. If the ball is in contact with a wall for 0.1 seconds, what is the magnitude of the force of the wall on the ball? Well, this is what I said earlier. You can set these two things equal to each other. P final minus P initial can equal force times time. So in other words, 38 can equal the force, which is unknown, times the time, which is 0.1. And I don't even care, again, I don't care about the direction because it says magnitude. But the force is going to be whatever 38 divided by 0.1 is. So in other words, 380 newtons. And that's just it for that. Any questions on that one? Okay, so just remember, the only thing you can possibly mess up, because it's pretty straightforward with the equations, the only thing you could really mess up is if you miss the negative sign. But now that we made the mistake once, we're not going to be making that mistake anymore, right? Okay, good. Good. Number 5. Superman, 100 kilograms, smashes through a brick wall. He was flying at 50 meters per second before the collision, and the brick wall exerted a force of 2,000 newtons for a time of 0.5 seconds. What is Superman's speed as he emerges from the other side of the brick wall? So hopefully you realize for this one, I need probably force times time because I give us a force and a time. So impulse J equals force times time. I'm also going to draw a picture of this because I always like drawing a picture. So here's Superman, and he has his cape. That's one of my better pictures. And then we have the brick wall. There we go, that looks like a brick wall. He's flying it with a speed of 50 meters per second. He has a mass of 100 kilograms, smashes through the wall, and emerges on the other side with some unknown speed. So since we want a speed, and I'm given the force times time, I have a feeling that once again, I'm going to have to say P final minus P initial equals the force times time. So P final, that's mass times velocity final. I can say 100 times V, which is what I'm solving for, minus the initial momentum, mass 100 times velocity 50, positive or negative 50?
Negative 50?
That's
Or,
positive. Superman's flying to
oh,
the
no,
right.
positive, sorry. Because
I
yeah,
forgive
it's
you.
going to the right.
Going to the right. Now, technically, could you have drawn this picture to the left? Yes, you could have drawn it to the left. Does that change the final answer? I promise you it's not going to. Because we're solving for speed, the final answer doesn't matter, positive or negative. Okay, we set this equal to force times time, which is 2,000 for the force and 0.5 for the time. And now we just solve for v. So that means 100v minus 100 times 50 is 5,000 equals 2,000 times 0.5 is 1,000. And now I just add 5,000 to both sides, so it's 1,000 plus 5,000. And then I divide by 100. So I get v equals 60 meters per second. That's funny. Can someone tell me why that's a funny answer?
Because he's going faster
Yeah.
than he started.
He's going well, I mean, if the calculator says 60, that's what it has to be. Unless you're saying I made a mistake. And if I were to make a mistake, there's no way I made the mistake that I said you'd make 2 or 3 times now about missing a negative. That's impossible. Does anyone see the mistake? We already talked about it. It's definitely positive 50. But let me tell you something. This wall is definitely pointing to the left for its force. Definitely negative 2,000 newtons. And that's what you got to be careful of. These problems are going to kill you. But hey, better to get it wrong in the summer than on the test. So that means that you're actually going to get negative 1,000 and a negative 1,000 here. And so your final answer is actually 40 meters per second, which makes a whole lot more sense because now he's slowing down. And before you close up the video, I just want to give one final message for the summer because after all, I'm doing this for free and you're at my mercy. And so now I want to talk about, again, why am I doing this for free? Anyone remember?
Because you want to be the greatest tutor of all time.
That's right. Check lesson 1 for physics and literally all my summer classes this summer. I say it every time. Because I do want to become the greatest. And why am I doing this for free? Because I want to give more value to you than I'm getting in return. And so even if you never decide to become a paying customer of Dan the Tutor, I don't care. Because I already know I made my difference. I put in my work and I know karma exists and it's going to come right back at me tenfold at some point in the future. And the reason I know that is because I remember when I very first started Dan the Tutor in the summer of 2020 at the beginning of the pandemic, I was literally working for free, just like I am now, except back then, this wasn't my full-time job. I was working at an engineering company for 40 hours a week. I was hating it, and I really wanted to do pretty much anything else that was a high-paying job. And ironically, of course, I turned to something that was literally free work until I made a name for myself. So for 6 hours a week during the summer, for the entire summer, no weekends off, including when I went to the hospital. That's a story for another day. But I still put in my hours, and by the time the fall came, finally I got a reference that someone very nice posted on the University of Delaware Facebook page, and I finally, after all this time, got my first paying customer. And then 1 turned into 2, and 2 turned into 3, and 3 turned into 10, and eventually, by the end of the year, the school year, I had 30 paying customers, and I made thousands of dollars, and it definitely made up for it. But as I like to say, I don't do this for the money. Obviously, the money's nice. I'm able to pay the bills. I can go on nice vacations. But even more important than that, I get to do what I love. And I get to make a difference in the world doing something that I'm passionate about and I know brings value to other people. So if you want my advice, whatever you do in this world, whatever you do for 40 hours a week, every week in your life, I encourage you to find something that you actually enjoy doing. Because believe me, I've worked with a lot of people at my engineering job, and many of them were in the same boat as me, where they didn't like what they did, but they couldn't get out of it. I was fortunate enough where I don't even want to say lucky in the sense that a lot of it was just me doing what other people before me did. In other words, where did I learn from? Well, I learned from other YouTube videos of people, how to become, a full-time tutor essentially. And I basically did what the video said, which was put in a lot of work and work for free at the beginning. And truth be told, it worked out for me. Now, of course, that doesn't mean everyone's journey is the same. It might not work out for you in the same way it worked out for me. But I will tell you this. I can say 3 years later after starting Dan the Tutor, I've never been happier in my 26 years on this earth. And I can't wish anything but the same for you. So with that, I leave you. Thank you all for attending this summer course, and best of luck whether you're going into high school or college in the fall. And I hope you get the grades that you want, and I hope I was able to inspire you and help you achieve your goals. So thank you, and bye-bye.